Before we begin, consider this. The storms on Earth that feel overwhelming are barely a whisper compared to what exists beyond our sky. Supersonic winds, centuries-long vortices, invisible magnetic shields, and gravitational boundaries that quietly decide the fate of worlds. This is the true scale of our solar system. Welcome to Relaxing Facts Studio, where we slow things down to reveal how extreme physics creates surprising stability. In this documentary journey, you'll discover how violent planetary forces, hidden magnetic defenses, and precise cosmic balance work together to make Earth calm, protected, and uniquely suited for life. Settle in, breathe deeply, and let the universe explain itself. Gravity is the invisible architect of our solar system, distributing angular momentum across every orbit with astonishing precision. Each planet, from Mercury to Neptune, carries just the right momentum to maintain a stable path around the Sun. Without this careful distribution, worlds could drift unpredictably, creating chaotic collisions that would destabilize the entire system. This fundamental force ensures that every orbit aligns in a cosmic rhythm, silently keeping Earth and its neighbors in motion for billions of years. Orbital resonance adds another layer of protection. Some planets and moons follow synchronized patterns, like Jupiter's moons locked in perfect orbital timing. These resonances prevent catastrophic collisions and guide countless asteroids and comets along safe routes. Even small bodies obey this natural choreography, creating a natural safety net that preserves the system's long-term order. The hierarchy of planetary masses further reinforces stability. Massive giants such as Jupiter and Saturn dominate the gravitational landscape, shielding inner planets from deadly debris and subtly controlling the movement of smaller celestial objects. Their immense influence shapes the orbits of asteroids and comets, making Earth's environment remarkably safe compared to the chaotic conditions in many other star systems. Modern simulations reveal just how delicate this balance is. Even minor shifts in a planet's position could have destabilized the solar system over millions of years. Yet, for 4.6 billion years, the system has remained resilient, allowing life on Earth to thrive. Studying these dynamics not only explains why our planet remains stable, but also provides a framework for predicting orbital patterns, guiding the search for habitable exoplanets, and understanding the hidden forces that maintain cosmic order. On Earth, hurricanes and tornadoes can feel extreme, but in the grand scale of the solar system, they are gentle whispers. Gas giants like Jupiter and Neptune host storms far more powerful, fueled by energy scales millions of times greater than anything on our planet. These enormous atmospheres store and release energy across layers thousands of kilometers deep, generating storms that can last centuries, dwarfing the brief, surface-limited tempests we experience. The absence of solid surfaces in these massive planets amplifies turbulence. On Earth, land masses act as natural brakes, slowing winds and breaking storms apart. On Jupiter and Saturn, there are no continents to disrupt the flow. Gas and liquid layers move unimpeded, allowing storms to persist indefinitely and grow to unimaginable proportions, spanning entire hemispheres and rotating faster than a jetliner could travel. Atmospheric depth further drives continuous chaos. These planets' atmospheres extend far below the cloud tops, with pressure and temperature increasing dramatically. Deep convection channels energy upward, sustaining enormous vortices and jet streams. Unlike Earth, which self-limits storms as energy dissipates near the surface, gas giants recycle this energy internally, producing near-constant turbulence that reshapes clouds in days and months. Even frozen worlds like Neptune generate supersonic winds, reaching speeds over 1,200 miles per hour. Despite receiving minimal solar energy, internal heat and chemical composition create extreme weather patterns that defy terrestrial comparison. Understanding these processes not only highlights Earth's relatively mild climate, but also provides insight into planetary physics, storm dynamics, and the extreme conditions that define other worlds in our solar system. Jupiter's Great Red Spot is not just a storm, it's a swirling colossus that has persisted for over 300 years, defying everything we know about weather on Earth. Unlike terrestrial vortices, Jupiter's storms rotate over a fluid system with no continents or surface obstacles to slow them down. This uninterrupted rotation allows winds to maintain incredible speed and stability, creating a vortex hundreds of times larger than any hurricane we've ever seen. The vertical structure of the storm is equally extraordinary. Recent measurements reveal that the vortex extends deep into Jupiter's atmosphere, reaching layers far below the cloud tops. Temperature and pressure increase dramatically with depth, feeding the storm from within and sustaining its energy over centuries. Unlike Earth's storms, which weaken as they rise and encounter surface friction, Jupiter's vortex remains anchored by this immense vertical convection. Internal heat flow is another crucial factor. Jupiter emits more energy than it receives from the Sun, and this internal heat drives convection currents that fuel the storm from below. Warm gases rise, cool, and sink again in a continuous cycle, providing a steady source of energy that prevents dissipation. This internal furnace is what allows the Great Red Spot to survive where earthly vortices would collapse within weeks. On Earth, even the largest hurricanes are fleeting because surface drag and limited energy sources naturally dissipate storms. Jupiter's combination of uninterrupted rotation, deep atmospheric layers, and internal heat creates a self-sustaining engine. By studying these extreme vortices, scientists not only understand gas giant dynamics, but also gain insights into the fundamental physics of fluid rotation, energy transfer, and the extraordinary scale of planetary weather beyond our own world. Neptune is a world of extremes, where winds race across the atmosphere at over 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic storms are fueled by a combination of internal heat and atmospheric dynamics, creating conditions that defy terrestrial expectations. Despite being nearly 3 billion miles from the Sun, Neptune generates energy internally, powering jet streams and massive vortices that persist for decades. One striking feature is the paradox of extreme weather with minimal solar input. Unlike Earth, where storms rely heavily on sunlight-driven energy, Neptune's atmosphere taps into residual heat from its formation and slow gravitational contraction. This internal energy is transferred through convection, driving colossal flows and sustaining supersonic winds that could strip a planet like Earth bare in minutes. Methane clouds play a critical role in accelerating these winds. As methane rises and condenses, it releases latent heat, feeding jet streams and generating vertical turbulence. These clouds also create striking blue hues, while acting as conduits that transfer energy across the atmosphere, amplifying storm intensity. Neptune's storms differ fundamentally from Jupiter's Great Red Spot. While Jupiter's vortex is anchored by deep rotation and continuous internal heat, Neptune's frozen environment produces rapid, unpredictable gales shaped by high atmospheric compressibility and extreme temperature gradients. The storms appear and evolve quickly, creating transient dark spots and shifting cloud bands. Studying these hypervelocity storms helps scientists understand not only planetary weather extremes, but also the physics of atmospheres under minimal solar influence, offering a window into the diversity of conditions possible on exoplanets far beyond our own solar system. High-pressure conditions in the deep atmospheres of gas giants like Saturn and Jupiter create weather phenomena unlike anything on Earth. One of the most astonishing is diamond rain. Carbon atoms are compressed under extreme pressures, transforming first into graphite and then crystallizing into diamonds mid-air. These solid gems then fall through turbulent layers, a process that is not only beautiful, but also a remarkable natural demonstration of physics at extremes. Hydrogen-rich atmospheres introduce unique phase transitions that govern this exotic precipitation. As pressure and temperature rise with depth, carbon, methane, and hydrogen interact in ways impossible on Earth. These reactions create stratified layers, each with distinct chemical and physical properties. Understanding these transitions helps scientists decode the internal dynamics of gas giants and their thermal evolution over billions of years. Ammonia water hail, sometimes called mushballs, adds another layer of complexity. These hailstones form as ammonia freezes and combines with water, creating slushy pellets that can grow rapidly while moving through convective currents. Mushballs contribute to unusual chemical cycling in the atmosphere, distributing compounds and altering storm dynamics in ways still being studied by planetary scientists. Exotic precipitation like diamond rain and mushballs also plays a role in planetary energy transport. Falling solids carry heat downward, while convection moves energy upward, creating feedback loops that power long-lasting storms and jet streams. These processes influence cloud formation, wind patterns, and even magnetic field interactions. By studying these alien weather systems, we gain insight into planetary physics, extreme chemistry, and the hidden mechanisms that make gas giants dynamic, violent, and fascinating worlds, vastly different from the calm skies of Earth.
Earth is encased in an invisible fortress, a magnetic field generated deep within its molten iron core. This planetary dynamo converts thermal motion into magnetic force, creating a vast bubble that extends tens of thousands of kilometers into space. The spinning, convecting liquid iron generates currents that align and reinforce the magnetic field, producing a stable shield capable of deflecting charged particles traveling at over 1,000,000 miles per hour from the Sun. The magnetosphere interacts constantly with the solar wind, a stream of charged particles ejected from the Sun. When these particles collide with the magnetic boundaries, they are redirected around the planet, preventing the atmosphere from being stripped away and protecting life from lethal radiation. Auroras, visible near the poles, are a visible side effect of this cosmic interaction, where some particles are funneled into the upper atmosphere, releasing energy as dazzling light shows. Magnetic shielding preserves atmospheres over geological timescales, ensuring that Earth retains oxygen, water vapor, and other essential gases. Without this invisible defense, solar wind could gradually erode the air we breathe, as happened on Mars after it lost its magnetic field billions of years ago. Planets that lose internal heat and stop generating a magnetic field become vulnerable, with atmospheres thinning and surfaces exposed to harsh radiation. Understanding Earth's magnetic protection not only highlights its rarity among planets, but also informs future exploration. Designing spacecraft and habitats for the Moon, Mars, and beyond requires accounting for fluctuating magnetic fields and radiation hazards. By studying planetary dynamos and their interactions with the Sun, scientists can predict magnetic stability, safeguard technology, and explain why Earth remains uniquely habitable in a solar system full of extreme environments.
Far beyond Neptune and the Kuiper Belt lies the Oort cloud, a vast icy frontier where the Sun's influence fades and the galaxy begins to dominate. This is the true outer edge of our solar system, a region stretching up to 2 light-years from the Sun. Here, gravity from the Milky Way subtly pulls on icy bodies, nudging comets and distant objects into elongated, unpredictable paths. Defining the boundary of the solar system is a matter of gravitational influence. Within the Sun's Hill sphere, objects remain bound, orbiting our star under its control. Beyond this invisible bubble, galactic tides, forces from nearby stars and the Milky Way's core, begin to outweigh the Sun's pull. At this point, comets and minor planets can drift into interstellar space, effectively leaving the solar system forever. The orbits of these icy wanderers record a history of past stellar encounters. Slight deflections in their paths reveal gravitational interactions with passing stars, hinting at the dynamic nature of our galactic neighborhood over millions of years. These frozen travelers serve as cosmic archives, preserving clues about the solar system's formation and the motions of nearby stars long before telescopes could detect them. This outer boundary is far from static. The Oort cloud shifts over time as new comets are perturbed inward, while others are ejected entirely. Its extent and density change with galactic tides, stellar flybys, and even interstellar gas. Studying this remote frontier not only tells us where our solar system ends, but also how fragile its gravitational hold is, offering a perspective on how Earth and its neighboring planets exist safely within a vast, dynamic cosmic environment. Earth's ability to host complex life is not just a matter of luck, It's the result of an exceptionally stable and rare planetary architecture. One key factor is the statistical rarity of long-term orbital circularity. Most star systems observed in our galaxy contain planets with highly eccentric orbits, creating chaotic gravitational environments. In contrast, the nearly circular paths of Earth and its neighbors ensure consistent distances from the Sun, allowing climates to remain relatively stable over billions of years. Outer gas giants like Jupiter and Saturn play an immense protective role. Their immense gravity acts as a cosmic vacuum cleaner, deflecting or capturing comets and asteroids that might otherwise threaten the inner planets. Without this shield, Earth could experience far more frequent catastrophic impacts, drastically reducing the likelihood of intelligent life surviving long enough to evolve complex societies. Climate predictability is another essential factor. Stable orbital patterns, combined with protective shielding, create an environment where seasonal cycles and temperature ranges remain within tolerable limits. This consistency allows ecosystems to flourish and supports the development of advanced cognitive functions. Rapid, unpredictable environmental shifts, common in many exoplanet systems, often inhibit the evolution of large brains and complex intelligence. When we compare our solar system to the chaotic architectures found elsewhere, the contrast is stark. Many exoplanet systems feature migrating giant planets or unstable orbital resonances, which can destabilize inner rocky planets and prevent long-term habitability. Understanding this unique combination of orbital stability, planetary shielding, and climate consistency explains why Earth is an extraordinary cradle for intelligence and why life as we know it may be exceedingly rare in the galaxy.
Exploring the extremes of our solar system provides invaluable insights for understanding planets far beyond our reach. Data from Jupiter's storms, Neptune's supersonic winds, and Saturn's diamond rain help scientists refine climate models by revealing how energy moves through massive atmospheres. These insights allow more accurate predictions of weather, temperature gradients, and convection patterns on planets both near and distant. The physics observed within our solar system also guides assessments of exoplanet habitability. By comparing orbital stability, atmospheric dynamics, and magnetic shielding, researchers can identify which distant worlds might support life. For instance, planets lacking protective gas giants or magnetic fields are likely to experience volatile climates or lethal radiation, limiting their potential for complex ecosystems. Understanding these factors helps astronomers prioritize targets in the search for life. Engineering space missions also benefits from studying planetary extremes. Probes like NASA's Juno or the upcoming Europa Clipper must withstand intense radiation, crushing atmospheric pressures, and supersonic winds. Insights from gas giants' environments inform spacecraft design, material selection, and mission planning, ensuring these missions survive and gather high-quality data. These lessons are critical as humanity plans to explore more hostile worlds, from Venus-like atmospheres to ice giant systems. Finally, our solar system remains the calibration standard for planetary science. Every extreme environment, storms, magnetic shields, icy comets, provides benchmarks to validate theoretical models.
By studying these extremes, we not only understand our cosmic neighborhood, but also build the tools and knowledge to explore distant systems safely and intelligently. The lessons learned here set the stage for discovering habitable worlds and preparing for the future of interplanetary exploration.
Thank you for joining us on this incredible journey through our solar system, exploring storms, magnetic shields, and cosmic forces that make Earth so unique. If you enjoyed this adventure, make sure to subscribe to Relaxing Facts Studio so you never miss another exploration. Share this video with your friends and social networks to spread the wonder, and hit the like button to help this episode reach more curious minds. Leave a comment below to tell us what amazed you most or the ideas this video sparked. Your support ensures the channel thrives and continues delivering fascinating, safe, and educational content on a regular basis.